In today's hyper-connected digital economy, predicting market behavior isn't just about forecasting sales. It's about understanding the hidden rhythms of consumer decisions, supply chain dynamics, and the volatile forces that shape e-commerce ecosystems. This video dives deep into a cutting-edge approach to multi-horizon demand forecasting, using a hybrid deep learning model designed specifically to capture the complex, non-linear, and time-varying nature of real-world retail markets. We're focusing on the UCI Online Retail II dataset, a rich repository of transactional data from a UK-based e-commerce retailer spanning 2010 to 2011. But here's the key. Unlike prior studies that mixed financial lending narratives with retail data, we've taken a clean, focused approach, defining our prediction target clearly. Per SKU daily demand or revenue for horizons of 1, 7, and 14 days ahead. This precision matters. It ensures we're not just predicting something, we're predicting what matters to retailers, how much of each product will sell when, and how that demand evolves over time. So how do we build a model that can handle this complexity? Our solution is a hybrid temporal neural network, a fusion of three powerful components: multi-scale temporal convolutions, a gated recurrent module, and time-aware self-attention. Let's unpack each. First, multi-scale temporal convolutions. Traditional models struggle with both short-term fluctuations and long-term trends. But here we use parallel convolutional kernels, small, medium, and large, to extract patterns at different temporal granularities simultaneously. Think of it as reading the market at multiple time scales: hourly spikes, weekly cycles, seasonal shifts, all in one go. Next, the gated recurrent module. Instead of relying on standard LSTM cells, we introduce a dynamic gating mechanism. This isn't a fixed gate. At each time step, the model decides how much memory to preserve, based on both the current input and historical context. This adaptive memory flow makes the model far more responsive to sudden shifts, like holiday spikes, flash sales, or supply chain disruptions. Finally, time-aware self-attention. This is where the model learns to focus on the right moments. Unlike vanilla attention, which treats all past time steps equally, our version modulates attention weights using a time kernel, a function that boosts relevance for periods close to holidays, weekends, or known seasonal peaks. For example, a sale on Black Friday gets exponentially more weight in the model's decision-making process. The result? A model that doesn't just learn patterns, it learns when those patterns matter most. Now, training this model isn't just about minimizing error. We use standard regression losses, but with critical safeguards. To prevent data leakage, we enforce strict time-based splits. No peeking into the future. Every training and validation window is rolled forward in time, mimicking real-world deployment. And we evaluate rigorously, using not just MAE or RMSE, but SMAPE, MASC, and THALES-U across all three horizons. These metrics together give a full picture: accuracy, scale invariance, and relative performance against naive benchmarks. We benchmark against a diverse suite of models: classical ones like ARIMA and Profit, standard deep learners like LSTM and GRU, tree-based models such as LightGBM, and state-of-the-art transformers, TFT, Informer, Autoformer, and NBATS. And here's what we found. Our hybrid model consistently outperforms all baselines, especially during peak periods, holidays, end-of-quarter spikes, promotional events, where traditional models often fail. But we didn't stop at performance. We conducted ablation studies, removing each component one by one, to prove each piece adds value. We also ran statistical significance tests, including the Diebold-Mariano test, to confirm these gains aren't due to chance. And yes, this work is fully reproducible. All code, data pipelines, hyperparameters, and evaluation protocols are open-sourced. Because real progress in AI doesn't come from black boxes, it comes from shared, verifiable science. So what makes this model truly special? It's not just that it predicts better. It adapts better. The architecture is built to respond to dynamic market conditions, not just learn from them. And that's where reinforcement learning comes in. We don't just train the model to predict, we train it to optimize. The model learns a policy that balances short-term accuracy with long-term reward, using a joint objective that combines forecasting loss, policy gradient updates, and entropy regularization. This means the model doesn't just react to trends, it anticipates them, exploring new strategies while staying robust to volatility. In practical terms, this translates to higher cumulative profit optimization, a metric we designed to measure real-world economic impact. Over time, our model consistently outperforms others in maximizing long-term profit, thanks to better inventory decisions, reduced overstock, and smarter promotional timing. Let's talk numbers. Across all horizons and evaluation metrics, our model achieves lower error rates, higher stability, and significantly improved performance during high-variance periods, exactly when businesses need it most. And when we look at the data, especially in Q1 and Q2 of 2011, when demand patterns shifted due to seasonal and promotional changes, our model maintains its edge, while others degrade. Why? Because it doesn't just fit the data, it understands it. This research isn't just about better forecasts. It's about rethinking how we model dynamic systems, especially in two-sided markets, where platforms, merchants, and consumers interact in complex, interdependent ways. Traditional models fail here. They assume linearity, stationarity, and independence. But real markets are none of those. Our model, by contrast, embraces complexity. It captures nonlinear dependencies, multi-scale temporal dynamics, cross-sectional interactions, and time-varying uncertainty, all within a single unified architecture. And the implications go beyond retail. This framework can be adapted to financial forecasting, supply chain planning, energy demand prediction, and even macroeconomic modeling, any domain where time, uncertainty, and human behavior collide. So where do we go from here? Future work should focus on scalability, making these models work across millions of SKUs, and interpretability, so we can explain why the model made a certain prediction. We're also exploring multi-agent reinforcement learning and meta-learning to further enhance adaptability, so the model doesn't just learn from history, but from experience, evolving its strategy over time. In conclusion, the future of forecasting isn't in bigger models or more data, it's in smarter architectures. Our hybrid model proves that by combining multi-scale convolutions, dynamic gating, and time-aware attention, we can build systems that don't just predict the future. They anticipate it, adapt to it, and help us act within it. This isn't just academic. It's practical, it's scalable, and it's already being used. If you're a data scientist, a product manager, or someone building systems for dynamic markets, this is the kind of model that turns data into decisions, and decisions into value. Thank you for watching. If you found this insightful, hit like, subscribe, and share with anyone who's building the future of intelligent systems. And if you want the code, the full paper, or a deeper dive into the architecture, check the description below. The research is open. The tools are ready. The future is now.